This is Steve Tatarunis, Technical Support Manager at Listen Inc. And if you've been following this Working From Home video series, you might recall the video that Devin Valancourt produced on sequence optimization. After that video was released, we received a few questions about optimization techniques for the step sign stimulus, particularly the step duration settings. Is changing these values just trial and error to determine the best settings for our test sequence? Is there a diminished return when going too far with these settings? So in this work from home video, we're going to look at the measurement confidence function, which can be found in the distortion tab of the harmonic track analysis editor. And while there is some trial and error involved in finding the optimum step size, this tool can help you understand the trade-offs between speed and accuracy in your test environment, thereby allowing you to optimize your Stweep parameters in the shortest amount of time. But before we do that, let's do a quick tech review on a couple of topics, the first one being frequency resolution. And true frequency resolution is determined by the analysis time, and we can represent this using this very simple equation, bandwidth times time equals unity. And because we need to measure for at least one cycle, an example here is to measure 20 Hertz, we need to measure for at least 50 milliseconds, and that comes back to our equation above. 20 Hertz times 50 milliseconds equals 1. Bandwidth times time equals unity. But the thing is, due to the settling time of our device and the windowing or filtering that we're doing in the FFT, we really need at least 3 cycles as a practical minimum to do accurate analysis. So for example, to measure 20 Hertz, we're going to need 3 cycles or 150 milliseconds of averaging time. Next topic is background noise, and to minimize background noise we need to filter or to average, and this video is going to focus on filtering. And the narrower the filter, the better signal to noise ratio, but the longer the measurement time. Just go back to bandwidth times time equals unity. In a Stweep, SoundCheck will dwell on each frequency step for either the minimum cycles or the minimum duration, whichever is longer. And if you only had minimum cycles per step, the dwell time for high frequencies would be very short, and the measurement time may not be accurate. If you only had minimum duration, the low frequencies would not contain enough cycles to be accurate. So using both ensures optimum accuracy throughout the frequency range. Above the transition frequency, the minimum duration is longer, and below the transition, the cycles per step becomes the longer time duration. And again, it all comes back to speed versus accuracy and what is more important to you and how do we find that happy balance. So any measurement has a level of uncertainty due to noise. Noise introduces a randomness to the level, so a measurement at best is only an estimate. But since we know the noise level, we can calculate the standard error of the estimated level using the measurement confidence feature in SoundCheck. Consider one measurement with a value of x and a standard error of sigma. The confidence that the true value will be within the plus or minus sigma values is as follows. Plus or minus sigma with 68% confidence, plus or minus 2 sigma with 97% confidence, plus or minus 3 sigma with 99.7% confidence. And these are the confidence limits in SoundCheck. The standard error for the fundamental, as well as every selected harmonic in our order, can be displayed. The standard error is calculated in the same units as the fundamental, and the resulting curve is based on one standard deviation. There's a choice of having standard error as a single curve or confidence limit as 2 curves. A noise curve can also be displayed, and this is the RMS level of the total noise at each stimulus frequency or frequency pair when measuring intermodulation and difference frequency distortion. So that blank screen tells me that it's time to switch over to SoundCheck, and I want to show you a couple of things over here. The first thing is I'm going to just open up a few virtual instruments, and over here on the FFT spectrum analyzer you can see that I have a very narrow x-axis range, 900 Hertz to 1.1 kilohertz. And I've made it that narrow because I'm going to be playing a 1 kilohertz sine out of the generator here, and I want to show you what happens to the FFT window or the FFT filter as we change the resolution time in the analyzer. So let's unmute the generator. And notice the filter width here at 50 milliseconds. And what happens is I increase it. So as I increase the resolution time, the filter is getting narrower and narrower, and you can imagine that's going to have a positive effect on rejecting any noise that might be present. And just as an example, let's introduce some noise to the measurement. So you can imagine how well a filter this narrow is going to reject noise versus a filter that might be significantly wider. So there's a little visual representation of what goes on as we increase our measurement time. Now let's open an example sequence. And this is a modified version of the confidence and noise sequence that comes in your SoundCheck installation. You can find it in the sequences folder in the subfolder called How To Examples. And as the introduction says here on the sequence note, the sequence demonstrates the capabilities of SoundCheck for estimation of measurement error and confidence limits. The sequence compares the results of 3 stimuli and shows the impact of the number of cycles and dwell time on the measurement precision. So this sequence has 3 different stimuli. One has 3 cycles minimum and 0 duration minimum. The other one has 10 cycles and 0. And the last stimulus has 10 cycles and 10 milliseconds minimum duration. And we're going to see how these changing parameters affects the measurement confidence. So I'm going to run this sequence up to a point and it's going to pause, and then I'm going to turn on some background noise and run it to the end. Let's take a look at these measurements before we turn on the noise and continue. So this is the result using just 3 cycles in the stimulus editor, and the confidence limits aren't too bad through the mid-band, but we can see that up here above maybe 7K, the lower confidence limit just drops like a rock. Here's the upper confidence limit. This is the fundamental, and down here we have the standard error curve. So at both endpoints of the curve, the limits get quite wide. Up here, probably because we don't have a whole lot of time spent at each step in the step sign, and down here just because the signal is getting into the noise floor of my measurement environment here. Things improve when we increase the number of cycles to 10. The limits are much tighter around the curve, the fundamental curve, and they're a lot tighter at the high frequencies, but about the same at the low frequencies, and that's what we would expect. And there's also been some significant changes in the standard error curve. And lastly, we have the 10 cycles and 10 milliseconds, and adding the 10 milliseconds vastly improves the confidence up at the high frequencies, and we can see this reflected by the upper and lower confidence limits, as well as the standard error curve, which is just sloping downward here. Nothing's really changing down at the low frequencies because of the noise in the room and the very low signal coming out of the device that we're testing. So at this point, I need to open up a signal generator and turn that on, and we'll run to the end of the sequence. And as you can see over here, the presence of the noise really degraded our confidence limits, particularly on the low side. Compare this measurement to this measurement, and the confidence limits are quite low, starting at about 200 Hertz and again dropping off at very high frequencies. The same here at the 10 cycle measurement, and even to a certain extent up here in the 10 cycle 10 millisecond. We can see a big difference in the standard error curve. And in these tables, we're also showing an average of the standard error curve. So we can just look at these values and just see quite a difference. 68 over here, 76 here, 42 here, 64 here, 35 here, and 63 here. So in the end, it isn't that difficult to get high measurement confidence on a fundamental measurement like I've shown you here, but the real challenge is extending that to your harmonics, and maybe that's something you can explore on your own time while working at home. So I hope this gives you a better understanding of how the measurement confidence feature works and how you can use it to optimize measurements made in your test environment. So thanks for watching, and stay safe, everyone.